Everything is working? The recording you have started or? Okay. So in today's ICTS string seminar, Ashok will tell us about his recent work on whether moduli expectation values, are moduli expectation values or parameters.
Okay, thank you. Okay, so let me begin by giving a general introduction to the problem that we will try to address. And so this comes from the following observation that many string compactifications have what are called moduli fields. And moduli fields for us will be massless scalars with no potential. And there are many examples of such moduli fields in string theory. For example, when you have a compactified string theory, then sizes and shapes of the compact directions can act as massless scalars. Okay, so those are moduli fields. Even in theories which are not compactified, like say 10-dimensional string theory, we have a dilaton, and the dilaton determines the strength of the interactions in string theory. So these moduli fields can take arbitrary values at infinity. And the question that we would like to ask is, do different asymptotic values of the moduli give different theories or different states of the same theory? And this is related to the question that whether there is a single string theory with many different states or there are different string theories altogether. Okay, so this is the kind of question we will be asking. Okay. Now this has a danger of being a philosophical question, right? The answer may depend on your perspective. Okay. So we'll try to make this a concrete question by fixing a criterion, okay, that we'll study to determine, that we can study to determine unambiguously whether the moduli are, whether which of the two possibilities is true, right? That whether different asymptotic values of the moduli give different theories or are the different states of the same theory. Yeah, everything is being done in target space, right? That if you think of the 10-dimensional string theory, then there is a field dilaton, right, whose expectation value gives a string coupling constant. And we will ask that if we take two different theories where the coupling constants are different, right, asymptotic values of the dilaton are different, whether they are to be thought of as different states of the same theory or different theories. No, we'll be having some asymptotic infinity. Otherwise, the answer is somewhat trivial, right? Because if the whole thing is compact, right, then the wave function will spread out everywhere. Yeah, so you'll have asymptotic space-time. I mean, we'll be working kind of spaces that we live in, right? Not in some abstract kind of space. Yeah, string theory, right? String theory, I mean, we construct string theory in a certain way, and you will be focusing on string theories, okay, with different values of the moduli, right? Say a string theory compactified on a circle of size 10 to the minus 20 or a circle of size 10 to the minus 40, right? So these will be like different asymptotic values of the circular radius. Yeah, these are different target space solutions, right? And they differ by how the fields behave at infinity. Right? Because in one case, we are considering the field taking one particular value at infinity. In the other case, we are talking about fields taking a different value at infinity. Okay, and we are asking whether these two should be considered as the same theory or different theories.
This problem has an analog apart from string theory.
Yes, we'll see. I mean, even in spin systems, this has an analog, right? If you have a spin up state and a spin down state, whether you should think of as different states of the same theory or different states of the same theory or different theories.
So when you say value, fields value, you're measuring the field somehow, like.
Yeah, coupling constant. The values of the fields determine the parameters, apparent parameters of the theory, right? So the dilaton expectation value at infinity, the dilaton value at infinity gives the coupling constant of string theory, right? So that you can measure by doing a scattering experiment, right? Yeah, so you can measure coupling constants, right? Similarly, the radius, what the radius becomes at infinity determines the spectrum, right? How heavy are the Kaluza states? So those are all data that you can measure at infinity. Okay, so let's be conservative and assume start by saying that, okay, let's suppose that there are different theories. Okay? That A and B will consider as two different theories which are characterized by two different asymptotic values A and B of the moduli. Right? Later on, we will try to see if it's appropriate to call them different theories or the same theory. And the criterion that we'll be using, okay, for calling B as a state of the theory A, okay, is that any experiment that we can perform in B, okay, can also be performed by an asymptotic observer in A. Okay. That imagine that we have this theory B which corresponds to certain asymptotic values, so string coupling equal to 1/10. Okay. We have a space-time where the string coupling is 1/5. Okay. Now we'll say that string coupling 1/10 is a state of the theory with string coupling 1/5. Okay. If any S matrix that you could measure, okay, for string coupling equal to 1/10, okay, you can also measure in the theory where the string coupling is 1/5. Is this clear? This is not possible in QED, that should be clear, right? QED has alpha equal to 1/137. Okay. You ask, is it possible to perform an experiment in QED where alpha is 1/110? 1/10. The answer is no, right? I mean, how can you measure a S matrix of QED, okay, with alpha equal to 1/10 if our theory has alpha equal to 1/137?
Isn't this statement equivalent of saying that there is some experiment that allows you to change the coupling?
Yes, it is equivalent to that, but I will make it more precise, right? That any experiment that you can do with one value of the coupling constant, you should be able to do in the other value, with the other value of the coupling constant.
127.
Yes.
This is a parameter, let's say, got given. So in our part of the universe.
Yes.
There may be another universe in which the QED coupling may be of a different value. I'm not talking about the consequences of that. It's possible.
Yeah. But
in theory, in some sense.
no. But can you measure it? Suppose we are in our universe, right? We have our experimentalists. Can you give the experimentalists a protocol which will measure the S matrix of QED with alpha equal to 1/10?
In my universe, there is no such QED.
Exactly. So that's the point, right? In string theory, it will be different. That's what I will try to see, right? Then in string theory, it will be different. Yes.
So suppose I have a ferromagnetic system.
Yes.
So there are, let's say, just Eisenberg, CPU. So then there are two possible ground states. So if the boundary condition is given by all spins up, then I pick up the up ground state, and if it is down, then I pick up the. So are these? So now so these are supposed to be states of the same theory.
We'll see. So we'll fix a criterion. That criterion is this, okay? That assume that the asymptotic spins are up.
Yeah.
Okay? If you can measure, okay, any property that you would have measured if the asymptotic spins were down with the system where the asymptotic spins are up, okay? Then we'll say declare that these are the same theories.
It will require too much energy to simulate the all spins down condition.
Okay, we'll see. We'll see. It will not take too much energy, but we'll see that it's still possible. Right? So I'll give that example, spin system. Okay. So here first let me explain what you mean by experiment. Okay, an experiment here will mean the kind of experiment that a real experimentalist can perform. Okay? Which means that we cannot demand that an experimentalist should measure things with infinite accuracy. Right? We say that, okay, we fix some accuracy. Okay? However small it may be, you allow some error, and experimentalists you have to make the measurement within that error. Okay, the error can be arbitrarily small but not zero. At the same time, the experimentalists cannot demand that they will perform the experiment, they will need infinite resources, right? They have to do the experiment with finite resources. Okay? So this is what we mean by experiment, right? And something that can be performed with finite resources, but in return, we don't demand that the experiment has to be performed with infinite accuracy. So from this viewpoint, right, what we can say is that the finite resources will mean that we need to do the experiment within a finite region in a finite time, right? So if your asymptotic conditions are that of B, okay, and if you are trying to make a measurement in that system, right, you will have to do it with finite resources in a finite time, right? Because we can't wait for infinite time. That's a realistic experiment. So from this viewpoint, we can see that we can call that B is a state of A. Okay? If A has a finite energy state that contains an arbitrarily large space-time region R, inside which all the fields are arbitrarily close to that of in state B. Okay? I'm not demanding that the space-time region R is infinitely large, okay, but one should be able to make it as large as one wants. Okay? I'm not demanding that the fields inside are exactly B, okay, but it should be made arbitrarily close to that of B, right? If I fix the experimental, if I fix how much error is allowed, okay, you have to, within that error, you have to make this close to that of in state B. So if in a theory where the asymptotic moduli are A, right, so this is at infinity, you can create an arbitrarily large region, okay, inside which the moduli are in state B, okay, then we can say that A indeed can measure anything that B could have measured, because in this region you set up your experimental apparatus, do the measurement, okay, and then get the data out, okay, and hence A and B will be declared as the same theory, okay, because if you can do this.
Constraint not to come inside of.
No, it can come inside, right? It can come inside, but ultimately it cannot stay inside, right? Because we'll be dealing with theory of gravity where as far as only observable is a S matrix, right? So A can send its instrument inside, do the experiment, get the data out, right? This is what is needed, right? You have to be able to send the instrument in, make measurement, and get the data out, right? So if you can create a large region inside which the state of the system is in B, okay, and if we are allowed to send in experimental apparatus, make the measurement and take the data out, take the experimental apparatus out, okay, then we can say, declare that B and A, that B is a state of A, right? Because anything that you can measure in B, you can also measure in A. This point is clear? We'll see. Boundary interface will not be actually interface. We'll see what happens, right? But we assume that you can somewhat, at least there are some things which can smoothly communicate across the boundary. Okay, so we'll see what kind of boundary we have.
And this finiteness of R.
Yeah, exactly. I mean, you can't demand that R is infinitely large, okay, because that will require infinite resources. Okay? But with a finite resource, finite but large resource, you can create, if you can create a large enough region, okay, then you can perform your experiment there and send out the signal.
Usually, like when you have a theory of gravity, like R doesn't make sense, right? If you go in the bulk, like what is the R? Like, let's say I tell you about a fixed radius.
If R is big enough, it makes sense, right? At the Planck scale, it will not make sense. After all, we are making sense of R, right? I mean, we are doing our LHC experiment without worrying about what you mean by R. So R has to be large enough compared to Planck scale. Okay? But the important point is that there should be the meta observer, right? The observer who is doing everything, okay, should be at infinity, right? That observer, it can come inside R, but it has to go out, which is as good as saying that it can send its instrument inside R and get the information out. Yes. Possible asymptotic values of the moduli. Now you are saying that suppose the asymptotic value is actually A, okay, and you create a very large region, okay, where the value of the moduli is B. Okay, then if you do an experiment inside B, right, and if the region is large enough, okay, then as far as that experiment is concerned, it will behave as if the asymptotic value of the moduli is B. Right? So that's the sense in which we measure something in A, right, where the asymptotic value of the moduli is A, but the experimental measurement will be as if you are measuring it in an environment where the asymptotic value of the moduli is B. Right? That's the point. So if we can create an arbitrarily large region where the moduli take value corresponding to B, right, then for an experiment that's going on inside that region, it's as if the asymptotic value of the moduli is B. Finite resources means that we cannot create an arbitrarily large region, infinitely large region, right? But we can create an arbitrarily large region, right? So finite resources means that you can't spend infinite time or infinite space, right, or infinite energy, right? That's so you can't make this arbitrary. You cannot make it infinitely large. Okay? But if somebody tells you that I want the result to this accuracy, right? You tell the experimentalist that I want the result to an accuracy of say 1 part in 10 to the 20. Okay? Then the experimentalist will have to tell you how large a region they need to create, right? So that the experimental results are accurate within 1 part in 10 to the 20. Right? That may require a very large region, right? Because so that finiteness of the region will certainly affect the experimental result, right? But as the region becomes bigger and bigger, okay, the effect of finite size will become smaller and smaller, and you have to make it large enough so that the experimental accuracy comes down to within 1 part in 10 to the 20. Right? So that's the finite resources. You don't need infinitely large volume, but you need large enough volume.
So you're saying
Exactly. Okay. But at every stage, no, you may need to change the region size also. If you need a more precision, right, then you have to make sure the finite size effects are not affecting your result, right? You have to increase the size as well.
And if you can do it for arbitrary size, given finite energy, but our finite size, then you would say it's part of the same theory.
Exactly.
And you are saying QED is an example where we cannot do this.
Yeah, QED, you ask an experimentalist to change the confines, create a box where the fine structure constant is 1/120, right? They'll chase you. Or if you can suggest a way to do it, right, then you are famous.
Can it like beyond the observable universe?
If QED is the theory, it cannot happen. You can consider extensions of QED, right, where the coupling constant is a vacuum expression of a scalar field. Within QED, you cannot do it.
Because the coupling runs. So at about 100 GeV,
But that will not be in a vacuum. Right? Yeah, right? So, I mean, you can change the effective coupling of QED, put medium and so on, right? But the environment will not be that of a vacuum, right? If you want to actually measure the a scattering experiment, low energy scattering, in vacuum at alpha equal to 1/20, right? You will not be able to do it in QED.
This is your distinction between parameter and.
Exactly.
So if I am able to see some other value in some localized region, then I will say that this is not a parameter.
Exactly.
And in QED, I will say it's a parameter.
Exactly. Yes.
I'm really worrying about the fact that the same theory can be in different phases.
But QED, there's no known, yeah. Yeah, different phases are like this spin up, spin down, right?
Yeah.
Or different, yeah.
There are also the values dependent.
Yeah, so different phases are also part of the same theory.
Yes, that's
Yeah, right. But you cannot change the standard model coupling to arbitrary value, right? It's not there is a phase of standard model where the fine structure constant is 1/20 or 1/150.
W goes on massively different, things massive.
But that is a different theory, right? I'm saying that it's not.
Determined by the wave of the scalar movement.
But see, if it's a wave of the scalar field, the experimentalists will be able to change it, right? By doing something.
That is worrying me. Yes or no, I don't know.
No, experimentalists can.
The point is whether it's doing infinite volume or not.
No, you can take an arbitrary large volume, right? Yeah, exactly. Think of our universe. In this arbitrary large volume, right, there is no mechanism by which you can change the QED coupling constant to 1/20.
from these things, that you will call as not parameters, right? Because now
Yukawa couplings are parameters. Yukawa couplings.
Yukawa couplings are
Parameters.
parameters. The masses. Okay.
Well, see the wave.
They contain both things.
No, the wave of the Higgs field is fixed in terms of the fundamental parameters of the theory. You have no choice on that. Right? If the field had no potential, then the wave could be arbitrary.
And suppose if A has disconnected regions.
No, it doesn't matter because if the theory is fixed, right, then the allowed values are fixed.
But it can be different under two asymptotic. If A has, let's say, two disconnected components. Like
Yes.
2D system.
Yeah,
system,
yeah.
system.
QED has two different, suppose you are putting QED on two different components, right? Two different components. But the QED coupling is fixed. QED by definition is given by Lagrangian, where alpha is 1/137. In this example, we will come, right? We don't have to consider different.
I can take one value in some asymptotic region and another value in another asymptotically.
Yeah, in this case, you are considering 3 plus 1 dimension or D plus 1 dimension flat space time. So there's only one asymptotic region.
And there cannot be a gradient on the asymptotic.
That will give infinite energy, right?
Yeah, so that's
Yeah,
not
that's not allowed.
But if they were disconnected, it could have.
Yeah, we are not considering disconnected, right? Disconnected is, not very useful for this discussion, right? Take a connected space time, right? And we are analyzing this question there.
Have similar properties as the boundary, even if it's different, even if it's disconnected paths, as long as they have similar, like the comparison is between A and B, right? Yeah. So, no, I'm trying to understand the possibilities of it.
Yeah, so disconnected is not useful because what will you do with a disconnected space time? You cannot access the other part anyway, right?
No, asymptotic is disconnected. Like in the spin system,
Yeah.
there are two, like they are not connected by a rotation.
No, they're connected. I mean, we'll come to spin system, right? In the next slide, I think it's going to come to spin system. So this is a normal QFT, right? This is what I mean, normal QFT, which is also spin system. Yeah. 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 We'll see what the obstruction is, and the goal is to remove the obstruction, right? We don't have to do explicit construction, but we also describe explicit construction. Okay. So let's look at normal QFT, right? Suppose in normal quantum field theory, there is a scalar field, okay, whose vacuum expectation value is not fixed, right? There is no potential for the scalar field, and hence the vacuum expectation value can be arbitrary. Then we can achieve this by simply creating a large region inside which the moduli take the value B, right? Take a scalar field which is outside here it's A, right? Inside it's B, and across this boundary, right? Here I have drawn it as a sharp boundary, but let's imagine that the scalar field varies smoothly from A to B across this boundary. So this will require a finite energy, okay? Because there's a gradient energy that will come. So with finite amount of resources, we can in principle create a configuration like this. Okay? And you can make this larger and larger by spending more and more resources, because you have to, as you try to make this larger, you have to increase the size of this wall, and that will cost more energy. Okay? But nevertheless, it's a finite energy. Okay? So now this, of course, is not going to last forever. Okay? So if you start with an initial configuration like this, then eventually the domain wall will start evolving, right? The domain wall will start collapsing. Okay? And as time progresses, the system will evolve and the wall will collapse. But if you are considering a relativistic quantum field theory, then the time that it will take for this wall to collapse is of the order of the size of the system, right? Because everything propagates at the speed of light. So if L is large enough, then we can ensure that we can do whatever experiment you want to do in B by staying in this region, to any arbitrary, any desired accuracy, right? All you have to do is to spend more energy so that the domain wall is larger, okay? So that the boundary effects are not important, right? The time for which it lasts can become large, right? So the experimentalist has enough time to do the experiment with the desired accuracy, and you are done. Okay? So in a quantum field theory, okay, if you had a scalar field without potential, okay, then the answer to this question is obviously yes, A and B are part of the same theory. Is this point clear? Right? Because in quantum field theory, you can create regions of this kind, okay, which last for arbitrarily long period. Okay, which can be arbitrarily large and which can last for arbitrarily long period.
So this addresses the symmetry breaking.
Yeah, this addresses a spin system, right? It could imagine the outside is spin up, inside is spin down, okay? And then this wall is going to collapse. Okay, but it will last, if it's a relativistic problem, then this collapse will take a time of order L. Now the problem in gravity, right? So what will happen in gravity? Okay, and this is where the argument comes in, the argument of Banks. Okay, so he gave two arguments why this is not possible in gravity. So first argument is that if we have a theory of gravity, then you have to ensure that the configuration we designed to create large pocket of B, like the one that we described last time, in the last slide, it does not go behind an event horizon. Right? Imagine that we create a big wall like this, okay? And you are trying to perform measurement. The observer is sitting at infinity. Okay? You can make a measurement inside B, okay? But if the data doesn't come out, then it's no use, right? Because our observer is at A. Okay, and we are talking about S matrix measured from the point of view of the observer at infinity. Okay, so being able to measure something inside B is of no use. So let's try to estimate whether that happens or not. So the energy of the domain wall will grow as proportional to its area, and in D space-time dimension, the area goes as L to the D minus 2. So for D equal to 4, it's L squared, right, which is the usual formula for the area. So if you have an energy L, energy E in this, then the Schwarzschild radius, there is a formula for Schwarzschild radius in D dimension, which goes as e to the 1 over D minus 3. Again, for D equal to 4, this is the familiar relation. The Schwarzschild radius is proportional to the mass. So if we want to substitute this value of E, we see that it goes as L to the D minus 2 by D minus 3. Okay. And for large L, okay, this is much larger than L. Okay. So what's going to happen is that as you are trying to increase the size of this region, okay, the Schwarzschild radius of this configuration, okay, becomes much larger than the size of the region, right? Because it goes as L to the D minus 3, D minus 2 over D minus 3. So it's behind an event horizon, and observer at infinity will not be able to get any data that you might acquire by doing an experiment inside this region.
So what is that you want to change the wave in some region, but you are creating a black hole?
Exactly, right? If you try to change the wave in some region, right, it will create a black hole. That's the obstruction.
This kind of a counting will change in ADS. Is that right?
Yeah, in ADS, in fact, things are much worse. We'll see. I mean, ADS, it doesn't, I mean, there is no hope at all. Okay, because there is a second argument based on ADS. But here itself, let me just say that it's not completely hopeless, right, this argument, because there is some way to get around it, for not for the spin system, but at least for massless fields without potential, right, moduli fields.
So Ashok, can I ask a question?
Yes.
What about the false vacuum and various transitions can happen in gravity, right? False vacuum to true vacuum and all those things. Coleman-Delucia.
Yeah, those transitions can happen in gravity, but if for example, you have two degenerate vacuum, see, those can happen because inside the false vacuum there will be ADS, right? So it's true that domain wall energy may increase, but you gain by having a negative energy density inside.
Achha, okay.
But if for example, you have two degenerate vacua, then you cannot create a large domain wall, okay, which separates the one vacuum from the other one, because then the domain wall energy is the only energy that is that is under consideration, and the domain wall energy will always create a Schwarzschild radius that is larger. Okay, it will go inside a black hole. So large domain walls, right, in a theory of gravity are not very useful in creating an arbitrary large region, okay, that separates two different phases of the theory. Okay, that's the lesson from here.
Yeah, thanks.
Okay, thank you. So in spin system, in quantum field theory, indeed, what you said, Gautam, is possible. But if you are considering a spin system in gravity, right, then there is a limit on how big a spin system you can, I mean, how big this spin down system you can create. Yes.
Since these are moduli.
Yes.
These are connected continuously.
Yes. Yes.
But then does one really need a domain code?
Yeah. So, yeah. So that's what I've discussed here, right? The smooth transition. Okay. So that way one can try to get around it is by making this as smooth variation, right? From A to B, you go as you do, so you vary smoothly from A to B. Okay? And the question is, what is the largest scale over which you can vary? Right? That is L. Right? It doesn't make sense to if the domain wall size is for L. Right? It doesn't make sense to make the thickness of the wall larger than L. Right? Then that will basically increase the domain wall size itself. Okay? So we can gain a factor of 1 over L, okay, by making the thickness of the wall of order L. Okay. So in this case, the domain wall tension will be given by this. So there is a grad phi square, okay, times the dr. This is the integral along the radial direction. Okay. So grad phi square you can make of order L to the minus 2. Okay. And the integral over dr, if you make it a thickness L, is of order L. So you get the domain wall tension, effective domain wall tension is of order L inverse. Okay. And if you want to plug back into the same formula, you can say the energy goes as L to the d minus 3, and the Schwarzschild radius, okay, which is e to the 1 over d minus 3, now goes as L. So this is saying that if you make the field very smoothly across this wall, okay, then the best you can achieve is that the Schwarzschild radius is of the order of the system size. Okay. And now it becomes a more detailed question as to whether the system is inside the event horizon of the black hole or outside the event horizon of the black hole. Right? So this is the question we have to address, because it doesn't give the answer yes or no at one go, but it tells us that there is a possibility that you can somehow match, right? That there is a more detailed comparison you have to do. Yes. We'll see that precision can be in this case, right? Will be very bad, but still can be made as accurate as you want. It's true that you will say, okay, it's varying very slowly, right? So that means the field, I mean, you have not really set the moduli equal to that of B, right?
The real B state, you are closest to that in a very small way.
Yeah, you will think that, but it will not be true. We'll see. Yeah, it looks like the precision will be very bad, right? Because you are making the thickness of the domain wall very big, right? So where is your B, right? It looks like it's some continuous interpolation between A and B.
So if you're using a link, that's impact. If you're using tan hyperbolic or something like that.
Tan hyperbolic is not what? Tan hyperbolic is like a finite thickness, right? But gentle means the gentleness has to be of order L, right? So that's the point. If you make the tan hyperbolic with a finite width, then you are back to the Banks problem, right? Okay. So the second argument, okay, that was given by Banks, and this is in the context of ADS, that if we think of anti-de Sitter spacetime, right? Here the asymptotic values of the moduli set the coupling constant of the dual conformal field theory. Right? For example, in type 2b on ADS 5 times S5, the dilaton field phi determines the string coupling constant. Okay? But e to the phi at infinity gives a coupling constant of the dual n equal to 4 supersymmetric Young-Mills theory, okay, which is a G Young-Mills square. Okay? And there it's clear that different G Young-Mills, okay, are actually different theories. Okay, in the same way that QED with different fine structure constants are different theories, and you cannot create a large pocket inside QED, okay, inside our universe where the fine structure constant takes a different value. Right? The same thing is true here. So here it's clear that different G Young-Mills are actually genuinely different theories. Okay? And then by ADS CFT correspondence, you would say that even in the bulk gravity theory, different values of e to the phi at infinity should correspond to different theories and not different states in the same theory. Okay? And we will see that this argument, in fact, is quite robust and will not be able to circumvent it. Right? If you circumvent it, then there is some problem, right? Because the dual CFT is certainly telling you that different asymptotic values of the fields are different, are describing different theories.
So, but, supposing one had the dilaton, okay, anti-de Sitter in general, in flat space, let's say, if we were having the rolling electron field, then you might expect that there is at least a time variation or some even possibly a spatial variation, because everything will be set by the electron, including the angles.
Yes.
In say string theory, let's say some all the standard model fields also. Then won't you say that the standard model fields also can have maybe a time varying or spatial?
Yeah. So when I made standard model, right, I meant standard model as standard model, not as part of string theory or a bigger theory, right?
Yeah.
Just in standard model, right? There is no dilaton field.
Yeah, but embedded in a bigger.
Yeah, embedded in a bigger theory, it can happen, right?
So here also, then you don't think of it as asymptotically, yes, but maybe you think of it as some brain living in.
Yeah, so there it will happen, and we will see that, right? But if the Banks's argument was based on asymptotically ADS spacetime, right? And there you clearly see that it's not possible, right? Because of this fact that there is an exact correspondence between n equal to 4 super Young mills and coupling G Young mills and the corresponding gravity theory in ADS. Yes.
If we waited for the black hole to evaporate,
Yeah.
is that really an obstruction and all?
Well, I mean, if you can wait for the black hole to evaporate, but what experiment you have done inside, right? To get the data out, it's not clear what protocol you should use to get the data out.
Surat's argument, everything is unitary available.
But whether somebody doing an experiment inside is a physical thing is not clear, no? From his argument, because his argument is based everything at infinity, right? From that argument, maybe this observer doesn't exist, right? So what are you trying to get out? Exactly.
I didn't understand this. Like,
Yes.
You are saying that it will be a different, like if the GYM is different, then it's a different theory on the boundary.
On the boundary. And the bulk or boundary theory are supposed to be exactly equivalent, right? For each Young mills, yeah.
What?
The ADS-CFT tells us the theory in the bulk is the same as the theory in the boundary.
Okay.
Right? So in the boundary theory, different G Young mills correspond to different theories. Then that should be the case also in the bulk.
Like that, where you have a domain ball on the.
Yeah, but those are two different boundaries, right? There you will think of the whole system as one theory, right? Which describes the RG flow from one to the other.
On the boundary, don't you have a domain ball on the boundary which extends into the boundary?
Yeah, so but I think that is a defect that you cannot create in the boundary theory. So this is a question of what kind of defect you can create in the boundary theory, and so those are not defects, right? Those are actually states in the theory, right? And then you can introduce external defects, okay, which are not part of the theory, right? So I think those domain walls, right, which cut the boundary and try to make two different G Young mills, those don't exist in the boundary as excitations in the boundary theory itself. Right? So if you are having the boundary theory at particular G Young mills, you cannot create those.
Yeah, but from the bulk point of view, these would be some finite energy.
No, not finite energy, because they are extend all the way to boundary, right? These will be infinite energy excitations. Yeah, that's the reason why they are not states in the boundary theory. So there will be actually infinite energy configurations.
Is it clear when you are allowing for the smooth variation across domain ball?
Yes.
Is it clear that like whatever the value I take is for the model?
Hmm.
If I just take A plus epsilon vector,
Yes.
then it will be allowed.
Yeah, then it should be okay. I think if you make epsilon to be sufficiently small,
If you allow epsilon,
yeah,
artificially,
exactly,
then at least just detail analysis, some region will be allowed.
exactly, yeah.
Isn't that enough to argue?
No, that's not enough. And we want to make sure that all values are equal, right? All A and B, arbitrary PRC A and B. Okay, so the goal will be that we'll give up ADS, right? We'll come back to ADS at the end. That we'll try to argue that in asymptotically flat spacetime, theories with different asymptotic values of the moduli correspond to different states of the same theory, right? In the sense I described, okay, then you should be able to create arbitrary large regions in the space-time, okay, where the moduli can take any desired value that you like, okay, which is the case of system, the theory B. Okay. Asymptotic values are kept fixed at some value A. Okay. So the strategy will involve two steps. Okay. So the first step will be to just identify some time, possibly time dependent classical solution. Okay. It doesn't have to be time dependent, but it's allowed, okay, in which the moduli take the desired value B at some space-time point P. Okay, we are not demanding much. Okay, we are not demanding that there is a very large region where fields are equivalent to vacuum and the value of the moduli is B, but just construct some solution, okay, where at some point in space-time, okay, the moduli take the desired value. Okay, that you imagine that you have a dilaton field which takes some value at infinity, and in the middle somewhere it takes whatever value you want. Okay. This we can imagine is perhaps not very hard, and we will see examples where this happens. But this is clearly not sufficient, right? This is necessary but not sufficient. And the reason that it's not sufficient is because for such a solution, the curvature and other field strengths may be non-zero at the point P, right? Which is what you don't want, right? Because you want really that you want to create a large region where the moduli are defined, but all the curvature and other field strengths are all zero, because you really want a vacuum, okay, at that state. You don't want some electric field sitting there or some space-time, curved space-time sitting there, right? You don't want any medium or anything, right? You really want vacuum, except that the moduli fields have taken a defined value. So the curvature and other field strength should be zero. Okay? And the second point is that what we need is an arbitrary large region where the moduli take values B, not just a point where the moduli take values B. Right? We want to make this region as large as we want. Sorry. And this is where the second step comes in. And that's the observation that if you take any two derivative action, like two derivative action means every term in the action has two derivatives, then this admits a scaling transformation, okay, under which the metric scales by lambda square, a rank k tensor scales by lambda to the k. So in particular, scalars don't scale, scalars remain unchanged. Okay. And under this transformation, the action changes by this factor over here. Okay. It's more or less straightforward to see. Okay. Basically, what happens is that the factor of lambda to the d comes from the square root of determinant g term in the action, right? Because g scales as lambda square, and the minus 2 comes because the two derivatives that we have in the action, they have to be contracted with an inverse metric, right? That's this minus 2. Okay. But because the action scales like this transformation, it's not a symmetry of the theory, but this acting on a solution generates a new solution. Okay, and physically what you are doing is that you take a solution and just stretch it. Okay, that's the meaning of this scaling of the metric. Okay. And under this transformation, any invariants, right, that contain 2n derivatives will scale as lambda to the minus n. Okay, so for example, the Riemann tensor square, okay, which contains 4 derivatives, will scale as lambda to the minus 4. Okay. If you take the gradient of the scalar field square, right, that will scale as lambda to the minus 2. And this means all of these invariants will vanish as lambda goes to infinity. Okay, so if you take the original solution that we had and do this scaling, okay, what it will do is that it will basically smoothen out the solution, okay, and around this point P, it will create an arbitrary large region, okay, where the curvature is almost zero, all gradients are almost zero, okay, and the scalar field takes value B, okay, around in this large region. Okay, because at P it was taking this large region, and that region you have basically stretched to an arbitrary large region. So this is related to Rishabh's question as to whether the accuracy will be compromised by letting this domain wall coming closer and closer. Right? If you think in these terms, right, and we will make it more precise. If you think in these terms, right, by stretching, right, you can actually create an arbitrary large region where the fields are arbitrarily close to B, and all curvature and other field strengths are zero. Only things without derivatives will survive, which is with the moduli, exactly. So the only scalars are the moduli, right? And the moduli basically will take whatever value it was taking earlier. Right? The gradient of the moduli will just remove. Okay, and this is where the difference with ADS comes in, right? The first step can be achieved both in flat space-time and ADS space-time, right? Just finding a solution where the moduli take the desired value is not very difficult, right? Take some time-independent plane wave or something where things oscillate and the moduli take values different from the asymptotic value. Okay. But the second step fails in ADS because the Lagrange, when you write down the action around ADS, right, there's a cosmological constant, and that's not a true derivative term in the action. Right? So if you have a solution in ADS, you cannot just stretch it and generate a new solution. But you can do this in flat space-time. And the other point, maybe I should have said that because of this property, right, string theory of course contains many higher derivative terms. Okay, but under this stretching, right, the effect of all the higher derivative terms you can ignore because they are becoming smaller and smaller because they are scaling by these. Right? So just the two derivative action is good enough for these solutions.
Sure.
Yes.
In this actually then, so cosmological constant is like a zero derivative term, right?
Yes.
So even in flat space, we could just have a scalar potential, not the moduli, but some other scalar field.
Yes.
That has some potential. So like then this scaling symmetry will not be there.
Yeah, unless that scalar field is set equal to 0.
Yeah, but
because topically, if you have a scalar field with potential, you'll set it at its minimum, right?
Okay.
And we are the fact that it's a flat, asymptotically flat space-time, then the potential at the minimum is 0.
But let's say it's some symmetry breaking potential, like some double well potential.
Yeah, so if it has a cosmological constant at the end,
okay,
right, then it will not work. Because we are assuming that space-time is asymptotically flat.
So whatever scalar you have with a potential, they should be at their minimum such that the value of the potential is 0.
Exactly.
At that.
That's right. Only then you can do the scaling.
Yes, exactly. It's the point that A and B have different cosmological constant also. Otherwise.
No. A and B don't have any different cosmological constant. A and B are dilaton, right? Yeah. The dilaton can vary by the flux. By the flux of this, some flux, right? In ADS5, for example, is the 5-form flux, which sets the cosmological constant.
That can be the same between A and B.
That can be the same between A and B.
Then why is it a problem to stretch? It's not a solution.
It's not a solution, right? If you take a solution and then do this scaling, the new configuration will not be a solution to the equation of motion.
I mean, the new solution will have a.
Yeah, new solution will have a defined cosmological constant, right? So you don't change the asymptotic. So there are two ways of saying it. One is that the action has this cosmological constant term and hence you cannot stretch it. Or if you insist on doing this scaling, then you have to change the cosmological constant, right? That means you change the asymptotic condition, right? Because flux has changed, which you don't want to change.
In the example of a scalar with a potential,
Yes.
You will not scale that scalar with this lambda scaling.
Yes.
The massive scalars will not scale.
Even the massless scalars, because the scalars never scale. Yeah, right? Because of this condition. So that's the reason why the scalars remain unchanged, right? The tensor fields get scaled. Okay, so here is an example, right? I think these are familiar examples.
There is some way to extend it to fermions, this lambda transformation.
Yeah, fermions, the point is you can extend it to fermions, but fermions are set equal to 0 in the vacuum anyway.
Yeah.
Right? So you don't worry about how the fermions are changing. Okay, so the example is charged black hole. Okay, this is a simple example. Charged black holes typically have varying moduli, and so you can use them to create regions where the moduli differ from their asymptotic values. Okay, and then this scaling will correspond to basically scaling up the charge and mass of the black hole. Okay, it doesn't change the scalar field profile, but it just stretches the solution to make it arbitrarily flat. Okay, it's the same physics that if you take a black hole, even neutral black hole, right? A very, very large neutral black hole, okay, the curvature near its horizon is almost 0, right? So it's as if nothing is there. Okay, so the same physics. So here is an explicit example. Okay, this is the black holes in type 2A and D equal to 10 that carries D0 brane charge. Okay, so this solution was written by Horowitz and Stroming a long time ago. So this is the form of the solution. It has three parameters, r plus, r minus, and this phi 0. So phi 0 sets the asymptotic value of the dilaton. Phi is the dilaton field, right? You can see as r goes to infinity, phi is equal to phi 0. And r plus and r minus, some combination of r plus r and r minus determines the mass, and a different combination determines the charge that the black hole carries. Okay. And we have, for regular solution, we have to have r minus is less than r plus. Horizon is at r plus, r equal to r plus, where it is a regular horizon. Okay. And the lambda scaling that I described earlier in this language will correspond to scaling r plus and r minus by lambda, r by lambda, and t by lambda, right? And you can see if you do the scaling, okay, so this takes this solution to a new solution with this different set of parameters. Then the metric just scales by lambda square, okay, everywhere, and this remains unchanged. And the gauge field I have not written, but there are explicit expressions for the gauge field. So the claim is that by taking this scaling and taking lambda to be large, we can create arbitrarily large regions in the vicinity of this black hole, where the moduli remain constant, but at a value different from the asymptotic value. So in particular, you can see that if you take r plus, r minus, and r to be large, right, then these quantities, right, the various things which appear here, remain almost constant over a region delta r, which is much less than r plus, minus, and r, right? Because if you change r by an amount that is small compared to r and r minus and r plus, right, all of these quantities change very little. Okay, so by taking r plus, r minus, and r to be very large, you can make sure that we have large enough region inside which the moduli don't vary. Okay, and all the curvatures and everything becomes arbitrarily small. But at the same time, around different values of this r, right, we have large regions that contain different values of phi, because you see the e to the minus 2 phi, right, its variation is small. Okay? But when r is of order r minus, right, it's different from e to the minus 2 phi naught. So the asymptotic value of phi was phi naught, but in the region, in this large region around r, okay, you can actually have phi that is different from phi naught, right, and not by a small amount, by a large amount. Is that clear? Right? Because r minus over r ratio can be of order 1, right, which makes it e to the minus 2 phi r different from e to the minus 2 phi r. In this case, it's always smaller. Yes.
Then that period.
Isn't that?
So let's say phi 1, which is smaller than phi 0.
Yes.
You'll call that as a state of phi 0.
Yes.
But you won't call phi 0 as a state of phi 0.
Well, if you can find another configuration where you can do the other way, you don't have to have the same black hole doing everything, right?
True.
You can create another region with something else, where the phi is larger. You can do, yeah. I mean, there is a different configuration that you can use. Right? I'm just giving this as one example.
But as a P is a state of the theory A. Would you also call A as a state of a theory?
Not necessarily. No. You have to check the other one. Because ADS is a state of the flat spacetime, but flat spacetime is not a state of ADS. We'll see. In flat spacetime, you can produce all kinds of ADS background. Inside, yeah, locally. Right? So all ADS S matrix elements are contained in the flat space S matrix element, but the reverse is not true. It's not something weird. It just says that ADS is more restrictive than flat spacetime. Okay, and in fact, we can go to the extreme, right? So if we take r minus to be close to r plus, but still less, right? And r to be also close to r minus, okay, but larger than r plus, okay, in this form, then you can see the e to the minus 2 phi, okay, if you do this, it's like 1 over 1 plus epsilon to the 7, and if you expand it out, it's the epsilon to the 3 by 2. Okay. So this corresponds to a large phi, right? As you take epsilon to be smaller and smaller, the phi becomes larger and larger. Okay, and however small you take epsilon, right, it looks like that here the solution is becoming singular, right? Okay, closer to becoming more and more singular. But if we scale up r plus and r minus, right, by a very, very large amount, you can just smoothen out the solution, right? So it's not singular. Locally, the curvature can be made as close to 0 as you like, and all scalar free gradients can be made as close to 0 as you like. Okay.
So this is some near extremal.
This is near extremal. Yes. Extremal limit is r plus equal to r minus. But it's singular. See, the D0 extremal D0 is singular. Right? So it's not a regular solution. That's why I don't want to go to extremal, but near extremal is good enough. Right? You can go as close to extremality as you like, and nevertheless make the background as smooth as you like by just scaling out the mass and the charges. At r minus, the solution is singular, right? And so if not rotating, yeah. At r minus, the solution is singular, and if you set r plus equal to r minus, then it's also singular at the horizon, right? But we are not doing that, right? The singularity is hidden by the horizon here. Okay, and we are even outside the horizon. Okay, and this is one important point that whenever we do this, right, we always remain outside the horizon because our goal is to make a measurement and send the data to infinity, right? Because the observer is sitting at infinity, right? So we never want to go behind the horizon. Yes.
Via this solution, you can explore any arbitrary value of phi.
Yes.
Starting from some phi now.
Yes.
Outside, you can make such a black hole.
Yes.
Explore any large phi.
Exactly. That's what it is saying. Right? So all of these phi's will be declared as states of the original theory. Yeah. Of the phi which had coupling constant phi naught. Right? In particular, right? Because this is strong coupling, so this is becoming phi is becoming large, that's strong coupling. And in this limit, in fact, this is equivalent to an 11-dimensional M theory, right? In fact, it's equivalent to 11-dimensional M theory compacted on a circle of radius, which is epsilon to the minus half. Okay? So by doing this, okay, taking the extreme limit, you can actually explore, even though the asymptotic observer is in a type 2 string theory, right? Small, no extra dimension. Okay? But by going close to the black hole horizon, okay, you can explore the 11-dimensional theory. Okay? So this means that in principle, the S matrix of M theory, okay, is contained in the S matrix of 10-dimensional type 2 string theory. Right? The exact S matrix, because this is, you can actually measure it experimentally, right? What the S matrix of M theory is by working in 10-dimensional type 2 string theory. Right? So this is saying that the M theory is actually contained in type 2 string theory at a fixed coupling. This is okay?
Can we make some statement about thermodynamics as well? The T0 brain thermodynamics therefore captures some thermodynamics of M theory.
We can do that, but I'm just thinking of this as a classical background, right? I mean, I'm thinking of experimental, right? Experiments, right? But if you are interested in a travel agency, right, you can actually create a travel agency where you say if you are living in 10 dimensions, you can say ask people if they want to experience 11 dimensions. Right? You can create a black hole, right? Take a spaceship and send people near in this region. They will not feel any curvature or anything, but they'll experience 11-dimensional physics. Right? But you can also study thermodynamics. That I'm not going to do that, right? This is just classical physics. And the classical description is valid because you can make the curvature as low as you want, right? Near the horizon of the black hole. All you need is a big resource, right? Because you have to create a very, very large black hole, right? If you want to go close to extremality, and at the same time you want to maintain that the curvature is small, right? If you keep a fixed mass and try to go close to extremality, the curvature is becoming large at the horizon. Okay, but then you scale up the mass, okay, to smoothen out the curvature. So if you have enough resources, you can create such regions.
Is this solution very special, or is it a general fact about near black holes that the compact direction is becoming large?
Not all near extremal black holes have this feature, but some do. Okay? Some near extremal black holes are very regular compact dimensions.
Isn't this what Banks and others use for the matrix?
Yeah, they used in fact not near extremal, they used the extremal one, right? And they used this for describing matrix theories, but their goal was to actually study the construct M theory in terms of D0 plane, right? Here you are not saying that you are trying to find a non-perturbative description of M theory, right? Yeah.
should be saying now that.
I agree, yeah. Yeah. I think they probably didn't think in this language, right? They are not thinking of the D0 when they talked about this matrix theory, right? In that paper, they never referred to this matrix quantum mechanics as the near horizon dynamics of D0 branes in type 2, right?
But after ADS-TIFR, people understood.
Yeah.
That they also-
Exactly, yeah.
But still.
Yeah, somehow, I mean, but the point is for any finite tension domain wall, his argument is very solid, right? So I think many things, I mean, his argument can be used to rule out many things, right? Because like there has been a lot of activity recently about this cobordism conjecture, which claims that between any two string theories there should be a domain wall. But even if that was true, it's actually not very useful because that you can create a domain wall. As long as the domain wall has finite tension, you cannot use it to create arbitrary large regions of the second theory. Right? So it's very specific to the case when there is a moduli space that you can do this.
Conjecture is for things which are not connected continuous.
Not connected continuously, yeah. Like for example, there is one conjecture that between type 2 and type 2b string theory, there is a finite tension domain wall. Right? That you can create a finite tension domain wall that separates type 2 and type 2b. But even if there was such a domain wall, okay, if you try to create a large pocket of type 2b inside type 2a using the domain wall, yeah, then Banks' argument will take over, it will go behind the horizon.
So
Yes.
this game theory vacuum
Yes.
is like a state of the D0 brane theory.
I'll say it is state of type 2a string theory, right? Because D0 branes are also states in type 2 string. Yeah. High energy state, yeah.
Vacuum in some high energy.
Exactly. Yeah.
So in any case, therefore, some kind of thermodynamics might show up.
Yeah, it should swap, right? But I'm saying just the standard S matrix. If you want to measure just the S matrix of M theory, right? You can do it in type 2 string theory, right? Because the asymptotic observer in type 2 string theory can actually send experimental apparatus in that region, do the measurement and get the data back, right? Because everything is outside the event horizon.
Maybe I can make a comment. It's maybe high energy from the point of view of the type 2 vacuum, but on the D0 brane theory, it's actually the infrared.
Yeah.
Right, because this 11-dimensional bubble is in the deep infrared of the geometry. The UV is kind of weakly coupled.
Exactly, yeah. But it's a high energy state from the type 2A viewpoint, right?
Yeah.
I mean, if you're asking what the experimental is in the type 2A string theory has to do,
Yeah.
they have to actually create a high energy state.
But then this papers by Masanori Hanada and his collaborators, they study thermodynamics by precisely studying the D0 brane quantum mechanics.
Yeah.
They work very hard to go to some low energy limit and try to reach the M theory limit. So that'll be a super low energy limit from their point of view. But the numerics are hard, but you're exactly right that people do study it. Thermodynamics, like this Masanori Hanada and other people, they've written a lot of papers about it. Yeah. And even these papers that Maldacena wrote recently about the S matrix in M theory, calculating the 3 graviton amplitude. I think there he is using this picture that to explain in modern language that the gravitons actually come in through this weakly coupled region of the D0 branes. Then they come to the M theory region, scatter, and then go back out. It's like this picture.
Okay, so the point is the same mechanism works for compactification to lower dimensions. I'll not discuss very much of this. And the main point is we can create large regions in space-time in which the compact dimensions and the dilaton can take the desired values in the vicinity of black holes carrying appropriate charges. So using this, one can show, oh, this is an important that just a single black hole sometimes is not enough. Not just single black hole, a single configuration is not enough. Sometimes you have to consider nested configurations, right? And what this means is that suppose in a theory of the asymptotic moduli A, we have created a large region where the moduli take value B. Then we can place a second black hole somewhere inside B, which can now produce a large region where the moduli take the value C. And the second black hole should also be made big, but if we take it to be much smaller than the first black hole, then from the point of view of the first black hole, the second black hole is like a probe. Okay, so the probe is outside the event horizon of the first black hole, so you can do all the measurements. And then the experimental apparatus is in the outside the event horizon of the second black hole, so that's also like a probe. Okay. And this nesting, okay, guarantees that as long as at every stage the n+1th black hole is outside the horizon of the nth black hole, okay, you are able to send signal to infinity. Okay. This is a technical point, right? It's not very important conceptually, but the point is if we take two black holes of equal or nearly equal size, okay, it's very difficult to determine which point in the vicinity of these black holes is outside the event horizon, because that's a global statement, right? I mean, we are asking that if you take a pair of black holes, right, which are, of course, undergoing dynamics, okay, and if you have a point in that vicinity, right, whether the light ray from that point will reach infinity, right, is a detailed dynamical question. Okay. But using this nesting, when the second black hole is much smaller than the first black hole and the third black hole is much smaller than the second black hole, we can avoid that those issues.
So I am considering these configurations.
Yeah, because of this, that if you use these nested black holes, then you can cover the whole moduli space of these theories in d equal to 4 starting from any given value of the asymptotic moduli. Okay, but a single black hole is not possible because it simply doesn't have enough parameters. Right? So, for example, in n equal to 8 theory has 70 dimensional moduli space, okay, and the number of parameters from a single black hole is at most 60. Okay, so a single black hole cannot generate all points in the moduli space, right? The different regions in the vicinity of a single black hole doesn't cover everything. But if you consider this nested configuration of black holes, you can show that it covers everything. Right? Anywhere in the moduli space you want to go, you can go. So that's the reason for considering these configurations.
Basically, it says that you can set any value to this all this 70 moduli space parameters, and then it will be state of the same thing.
Exactly. Right? Because any other point can be gotten from this, or the starting point. So for n equal to 2 theories, the analysis is a little bit more complicated, but let me not get into this. Okay. We have to use other configurations. Okay. But the upshot is that using all these ingredients, you can reach any point in the moduli space of n equal to 2 supersymmetric string theories, starting from any given asymptotic value of the moduli. Okay. And this is important because what is known is that n equal to 2, the Calabi-Yau compactifications of type 2 string theory, okay, are all in the same moduli space. Okay. You can take type 2 on different Calabi-Yaus, okay, and there are these various topological changing transitions which are known as flop transitions and conifold transition. Okay. Using that, you can go from any Calabi-Yau to any other Calabi-Yau. Okay. So what this is saying is that if you have the access to the S matrix of string theory in a particular Calabi-Yau background for particular size, shape, dilaton, etc., okay, you have access to the S matrix of type 2 string compactification on any Calabi-Yau, okay, of any size and shape, because all of these are in the same moduli space, right? You can create pockets in the theory where you have a different Calabi-Yau with different shape and size.
Does that make all points of the string landscape to be states of a given of the same theory?
That's what I would like to have, but so far that has not been achieved because n equal to 8, n equal to 4, and n equal to 2 are in different moduli spaces. And then there are various flux compactifications which are in apparently different moduli spaces, right? So the next goal will be to try to connect these somehow.
Right, topology chain, you can create different collaborators in the bulk.
In the bulk, yes.
How is this smoothly connected? It's not smoothly.
It is smoothly connected because what happens is that at some point in the moduli space, you get extra massless fields, right, which are not part of the moduli. Okay, and once you have extra massless fields with vanishing potential, you can switch on the vacuum expectation values of those, and those you can reinterpret as if you are in a different Calabi-Yau. Exactly. Yes. That's a conjecture that that's a conjecture in mathematics that all Calabi-Yaus are related by flop and conifold transition, right? And the flop and conifold transitions are related by connecting smoothly in the moduli space.
But this connection doesn't happen at the supergravity level, right? This smoothness.
It doesn't happen at the supergravity level, but it happens at the effective field theory level. right? So what happens is that in the supergravity level, you have a moduli space,
Yeah.
right? You move in the moduli space, then you find that at some point in the moduli space, you get some extra massless states, which are not part of the original supergravity, right? But once you have the extra massless states, then you can consider field configurations where those extra massless fields are excited, right? You can create, for example, the plane waves where the massless fields vary. So earlier they are 0, now in a given new configuration, they are not 0. And that corresponds to going into a different Calabi-Yau.
But that you can describe at the level of the two derivative theory.
Yeah, you can describe at a level of two derivative theory, right? Because once they have become massless, then you can describe them in a two derivative approximation.
Because you want the lambda scaling to still persist.
Exactly.
When you're doing
Yeah,
this.
yeah, because you want to, every time you should be able to stretch it, right? So that you make as large a configuration as you like, right? And clearly, if you have to go farther and farther away in this Calabi-Yau moduli space, you need more and more energy, right? Because you have to start with a very big system, create a big region inside that, then create another smaller but still big region inside that, and so on. Right? These kind of nested configurations.
What does it mean at special values of the moduli? You get more massless fields.
Yes.
What does that mean for the profile of the mass? What is it outside? If
What?
I'm varying the moduli in the bulk,
Yes.
does that at some special locations in the bulk it takes those special values?
Yes,
Then
that's right.
I have more massless fields.
Exactly.
And I turn them on also. I give them
Yeah. So once you have created a large region where you are at those special values, right? In that large region, these other fields are massless, right? Yeah.
What are they outside? They're zero.
So outside they will be 0. Yeah. Because they have a mass, right? So they'll be they are set equal to 0 because they are the minimum of the potential. So they have a potential which vanishes at these particular points.
This also has a domain wall.
Not exactly a domain wall. These are all smooth domain walls, right? Because the scalar fields are varying smoothly, right? In some region, you come to the desired value of the moduli. In that region, there are extra massless states, right? In the original solution, those massless states are not there, meaning they are set equal to 0 because they are massive, right? So as you continue, they are still 0 here. Okay? Now you consider a small pocket here, right, where those massless fields are non-zero. Yeah, they are smoothly non-zero, exactly. They are outside they are 0, but inside there is some ball in which they are non-zero. Right? And that corresponds to going into a different Calabi-Yau.
From the supergravity perspective, say you are not in the special points, then you have there is modular fields and scalar fields and all the other fields that are there. But if you are on those special points, in the supergravity action, there will be other like the scalar field terms.
Exactly.
And then that would be like a different Calabi-Yau.
Exactly.
What was the obstruction I did to writing a two derivative action? If
No, massive fields. Right.
Higher derivative.
No, they have 0 derivative terms, right? Potential mass term is 0 derivative, right?
I was worried that these usually some smoothenings happens by using the full power of string theory. That means not just 2 derivative, but 4 derivative, 6 derivative terms are needed. So that is not needed here.
Yeah, we wanted all of these, right, have a description in the low energy effective field theory, right? It's basically what happened. The physics is stringy, right? What happens is that where are these extra massless states coming from? Some D3 brain wrapped on a cycle, 3 cycle is becoming massless because the 3 cycle is collapsing to 0 size. Yeah, some particular cycle, right? So that's why the extra massless states are coming in. But once you know that there are extra massless states, you can write the effective field theory for those, right? And then you can switch on the expectation value of those.
Chief, I have a sequence of top transitions or chemical transitions.
Yes.
So at every such transition, I have new massless fields coming up.
Yes.
So if I want to have a supergravity to begin with, then I have to have all these new massless fields in anticipation in my original.
No, that's not, we are not demanding that, right? You don't have to have one action which describes the whole thing, right? We can do patch by patch. We use one action to construct this configuration, right? And then inside this configuration, you find that there is a defined action which is useful. We just use that action. Okay? See that? Exactly. Local patch by patch transition. Exactly. Right? We don't have to do a global. We are not trying to do a global description. Right? It's a question of whether the physics of scattering amplitude in a given a defined Calabi-Yau is encoded in this, right? And by this you can, in principle, tell an experimentalist what is it that you have to do, right? To measure the S matrix of a Calabi-Yau, say 100 steps away, right? That you create this black hole, this kind of configuration. Inside that you create this kind of configuration and so on, right? But the point is all of these, right, these whole steps are designed in such a way that you never encounter a horizon, right? That you can send back the final experimentalist, right, where the environment is that of a Calabi-Yau which is 100 steps away, can still send signal back to infinity, right? Because that's what we need, right? The asymptotic observer we are not changing. Asymptotic observer is sitting at infinity of A, okay? But we want to get the data for the S matrix from other regions.
You also mentioned as is n equal to 2 supersymmetric and n equal to 4 supersymmetric. They are in different.
Yes. Right now we don't know how to connect them.
Is it not like if you compactify on T6 you get n equal to 4 supersymmetric?
Yes.
Then
Heterotic on T6 is n equal to 4. Heterotic on T6 is n equal to 4. When I say all Calabi-Yau or all non-trivial Calabi-Yaus, right? Type 2 on Calabi-Yau threefold.
Okay, so T6 is not related.
No, T6 is not, you are not, no. At least we don't know of any relation.
Different Calabi-Yau have different moduli.
Yes.
How are you splitting?
Because you are getting extra massless fields, right? Yeah, which will also act as moduli. Exactly. Right? And sometimes some massless fields might disappear, right? Once you switch on the vacuum expectation value of some these additional massless fields, right? Some fields which are massless earlier can become massive. Right? Imagine it's coupling like phi square, h square, right? As long as h is 0, phi is massless, right? But once you give vacuum expression value to phi, h becomes massive. Okay? So these kinds of transitions keep taking place. That's the way you change the number of moduli as on this way.
This is not a degenerate process in the sense of topology change.
No, it's not a degenerate process in the sense that it has a perfectly good low energy effective field theory description, right? If you try to integrate out some of the massless fields, then it looks singular, right? But once you include all the massless fields in the description, then it's a perfectly smooth process. Exactly.
I mean, configuration is smooth. Calabi-Yau will still be similar.
But the physics is not singular. That's the point, right?
Yeah, the 4D.
Yeah, exactly. Okay.
We'll discuss the last point about the finite time not measuring this asymptotic value. What is this?
Yeah.
How this one?
Oh, yeah. See, this is the point that suppose we are in such a universe, right?
We are in what?
Such a universe. Okay, and we are suppose living in n equal to 2 some Calabi-Yau, right? And we want to know if we have say explored up to 1 million light years, and we have found that the asymptotic value of the scalar field is this, right? But there's always a possibility that we are inside a region, right, which is like this pocket of a defined Calabi-Yau, right? So in any finite experiment, we cannot determine what the asymptotic value of the moduli is, right? So it's going the other way, right? Just like from any asymptotic value of the moduli, you can produce arbitrary large regions with a defined moduli, right? It also means the other way, right?
So here you mean that the person is inside the pocket.
Yes.
He's trying to measure what he thinks is asymptotic.
Exactly.
But he's really inside some other big.
Exactly, right? And the point, because there's a limit on how big this region can be, right? You can never be sure that the asymptotic value of the moduli that you are measuring.
Kind of assuming that the values of A and B are themselves somehow measurable. Because the outside guy was sending in people to measure B, right?
Yeah.
But
so you're assuming that there is some meta observer, right? Who is the genuine asymptotic region. But what this is saying is that asymptotic value actually is somehow not a measurable quantity, right? So that's another way of saying this, the different asymptotic values are really part of the same theory, right? Just like from outside, I mean, abstractly, if you had some asymptotic observer, right, you can measure any S matrix, right? This is saying that if you are living in some region, finite region, and if you think that you have measured the asymptotic value, that may not be the correct asymptotic value, right? So that's another way of demonstrating the same thing, that they are really part of the same theory.
Suvrat and Alok have paper about saying something like asymptotic charges cannot be measured in finite time. Is it related to this? Do you know?
Yeah, these are not really charges, so I
Okay.
don't know that it's related to this.
Okay.
Right? The asymptotic values of the moduli are not quite the charges. I think their thing was probably more complicated.
Okay.
That's my feeling, but
Because there was some confusion between the Berkeley group kind of saying this is not true or something. So I thought there was
yeah. So this is not, I mean,
Okay,
these I think we shouldn't think in terms of charge. Okay. So ADS, we have already seen, right, that the scaling argument doesn't work. Okay, but one could nevertheless ask that could you use some other means to construct configurations where an arbitrary large spacetime region of the moduli differ from the asymptotic values, right? We didn't prove a no-go theorem. We just said that the original scaling argument doesn't work in ADS, right? Because they have the cosmological constant. Was there a question? No. Okay. Okay. Yeah.
Regarding the class point.
Yes.
We can also, we can never be sure of the vacuum of you're saying.
Vacuum meaning we are in, suppose you are living in a universe, you have measured what we think is the value of the scalar field, right? Yeah. But we can never be sure that that is the correct asymptotic value of the scalar field. Because you have finite resources, we cannot explore all the way up to infinity, right? And the fact that the theory contains a state, right, where you can create an arbitrary large pocket where the moduli take different value correspond to the asymptotic values, right, without us being inside the black hole, right, means that you cannot really determine what the asymptotic value is.
For all we know, we are inside a black hole.
Well, if you are inside a black hole, of course, then asymptotics doesn't exist for us. Yeah, then the asymptotics doesn't exist for us, right? Then for us, the asymptotics is the horizon. Right? Yeah.
Is that like saying can be many canonical purification of state? If I measure something in some local region, I may not be able to say what is the value at asymptotes or.
Yeah, but I think I'm not thinking in terms of purification. This is not, it is pure classical. Right? All you are saying is that the theory admits a configuration, right, where you have an arbitrary large region, okay, where the moduli fields differ from the asymptotic values. Okay. Nevertheless, there is a horizon that encloses this. Right? Even though so arbitrary large region means you have to construct arbitrary large energy, but the scaling is such that you are still inside, you are not inside a event horizon.
But you are measuring the expectation
by measuring scattering amplitude, because expectation value of phi is a scattering, those are the parameters of the theory, right? What I think are parameters. So dilaton, for example, controls the coupling constant, right? So you are measuring the value by scattering, right, and seeing what the coupling constant of the theory is.
This is in contrast with standard model or QED, where just measuring here we know what the fine factor cost.
Yeah, because there is no scalar field, right, whose vacuum expectation value is fixing the fine structure constant.
Cost to ask about this vacuum. Like, can we be sure that we are in like vacuum? That probably we could.
No, we may not be in we may be in false vacuum. That's certainly possible. Right? Particularly since we are in de Sitter, we are not in supersymmetric theory. Most likely we are in false vacuum.
So changing the moduli value doesn't affect that.
See, we don't have a moduli. Right? Our world doesn't have a modulus, as far as we know. Right? So here you are talking about theories which have modulus.
I'm saying like if we change, say we are in the false vacuum and we change the moduli, it doesn't matter, we will still be in that vacuum because moduli.
You are assuming that you are in a false vacuum and we have moduli.
Yeah, we have moduli and we change the value of moduli.
Yeah, then you will still be in a false vacuum. Yeah, because the point is the false vacuum and the true vacuum are separated by some finite barrier, right? Moduli don't take us across the barrier. Yeah.
You cross one brain and the flux jumps by a certain amount.
Yeah.
And then again and so on. So you can be in between two such brains which are very far apart, And so of course all of these regions are in the same theory because you just separate.
Yeah, except that the branes, you cannot have parallel branes. That's the infinite energy, right? So you have to wrap it up.
Yes.
So that's the domain wall,
Okay.
right? And that has this problem that it will be inside the event horizon. So yeah, so it's not completely clear. I mean, this is something that I have been discussing with Sandeep, that whether there's any way to avoid this. Right? Basically, what you need is the domain wall tension has to be made parametrically small, right? Then you can go to that region and try to create a large domain wall, but it's not clear whether it's possible or not. Yeah, so the independent way to see what the difficulty is in ADS, right? That is light crosses ADS in finite time. Okay? So the argument, one of the arguments that we are giving earlier is that if we create a large domain wall, right? This is irrespective of black hole, before we discuss formation of black hole, that if we create a large domain wall, okay, then inside this, we have some other vacuum, and it will take at least a time of order L, if L is the size of the domain wall, for this wall to collapse, right? So you have at least time of order L to do your experiment. But in ADS, light crosses in finite time. Okay, so however large a domain we create, it could just collapse in a finite time instead of lasting for time of the order of the system size. Right? So here the limitation is basically the ADS scale. Okay, so you expect that in ADS we cannot have we cannot perform an experiment with infinite accuracy, with arbitrary accuracy, okay, by creating a large region. Okay, so here is an example that you can see that the domain wall collapses in a finite time. Okay, let me skip this here. Okay, so let me go to this further observation, right? And this comes to Kaustub's question whether if B is the state of A, whether A is the state of B. Okay, and the point is that even though in ADS, different asymptotic values of the moduli produce different theories, all of these actually can be thought of as states of string theory in flat spacetime. Okay. So here is an example. Consider type 2 or type 2B string theory on T6 times R31. Okay. And in this, we can find configurations, okay, involving black holes, which create an arbitrary large regions in which the size of T6 becomes arbitrarily large. Okay, because you can reach anywhere in a moduli space, right? So you can reach points in the moduli space where the T6 becomes arbitrarily large. So it's effectively as if you have a 10-dimensional space-time, right, in some region of space. And now we can consider a stack of n D3 branes, each wrapped along some T3, which is part of T6. Okay. From the asymptotic observer's viewpoint, okay, these are D3 branes wrapped on compact directions, so just some particles. Okay. So what the asymptotic observer has to do is to first create this black hole system and then throw in some particles of appropriate charge, okay, near the black hole, okay, so that it creates a stack of n D3 branes.
This is a finite energy thing.
This is a finite energy thing because we take the infinite size of T6 to be large but not infinite. Right? Again, everywhere you are thinking of finite resources, so you do experiment with finite size. Right? So large size of the D3 brane, but they are, because they are wrapping this compact cycle, they have finite mass. Okay, so this is a finite energy configuration. And so here the near horizon geometry will be ADS5 times S5, and any experiment that you might want to do in ADS5 times S5 can actually be done now in type 2 on T6 times R31. Right? This is the asymptotic space time, and you can create a subsystem, okay, where it's you have ADS5 times S5. And in fact, following this logic, one can show that the same theory contains all of these. Type 2B string theory on ADS5 times S5 with any value of dilaton and any amount of RR5 form flux, or M theory on ADS4 times S7, or ADS7 times S4 with any amount of flux. So you basically blow now all 7 cycles. Right? Think of this as M theory on T7, and you can go to a region of the moduli space where the T7 is large, okay, and then wrap appropriate M2 branes or M5 branes along the appropriate cycles of the torus. So all of these, right, which are the classic examples of ADS CFT, okay, you can create inside just compactification in 3+1 dimensional, okay, type 2 string.
You can also create the ADS black holes.
Yes, you can. Yeah, the ADS black holes will mean that you don't go extremal D3, but you take some near extremal D3. That will be like ADS black hole.
What does this
What does what mean?
The first statement, type 2B ADS, that's already dual to N equals first order.
Yes.
Does it mean type 2A on T6 plus R31 already contained in
Yes.
this?
All S matrix elements when N equal to 4 super Young wheels is contained in that theory. Exactly.
Similarly for all.
Yeah. ABGM, symmetric product or before all of these. Yeah.
I think
In the S matrix of type 2 answer.
I don't know.
Is it previous?
I think we had this maybe brief discussion at some. It's actually interesting to ask the question the other way. What does this mean for duals of flat space gravity? It is telling you that the duals of flat space gravity have to be much wilder than N equal to 4
Exactly.
super N.
This
Yeah,
will contain all
because
of
they're like much more rich, much more wild.
Yeah, that will be my last conclusion.
Statement that you said before that G Young is different theory.
Yeah, they are different theory if you just think in terms of Young mills. But in type 2, a string theory on T6 times R31, right? They are all part of this.
So states in G angles of one value and states in G angles of other value are all states of
Type 2 and
Type 2.
exactly.
What is not a state?
Well, I mean, maybe you can, well, as I said, N equal to 2 supersymmetric theories, right, are as yet not a state of this, right? Because you don't know how to create them in this theory.
But you can just further compare.
Pardon? No, unit Calabi-Yau, right? I mean, the two.
Unit.
Yeah, Calabi-Yau, exactly. That you don't know how to do. Duals of what?
Like holographic dual of these theories
Yeah.
are different.
They are different theories, yeah. Because these are different states of type 2 and T6 times R31, right? So the holographic duals of these are different. So that's the sense that in no sense the type 2 and T6 times R31 is a state of this. Okay, but these are all states of type 2 and T6 times R31.
Okay.
Right? So these are just, so holographic duals of these are all different, right? And those different theories are all states of this.
It's counting a subsector of the Hilbert space.
Yeah, it's just a subsector of the Hilbert space.
You direct sum all this Hilbert spaces.
It may not give the whole theory. Yeah.
That is like a direct sum of all the 5 CFTs.
Yeah.
And
Yeah.
all that should be in the dual CFT.
Yeah. Yeah.
There's the dual.
Exactly.
non-CFT.
Yeah. It's not direct sum, but also you have to integrate over all Young mills, right? So it's all possible fluxes. Yeah. Yeah. So here is a pictorial description, right? That what this is saying, right? That if you think of string theory in flat space time, right? That is somewhere here. You just explore in that flat space time. You can create different regions where there are different moduli and also these different ADS. Okay? And these ADS are like deep wells that you create in this background. Okay? And the idea is that if you want to explore ADS, physics of ADS, right? You can do it from asymptotic region, okay? Simply by probing arbitrarily deep into these wells, okay? But not all the way, right? The theory on ADS 5 times S5, right? Or other ADS, right? Those are decoupled theories where you go all the way down to the horizon. Okay? Once you go all the way down to the horizon, from there you cannot come back. Okay? But if you are demanding that we should be able to measure things to up to a given accuracy, right? However accurate you demand, okay? Then you don't need to go all the way down. Okay, you can go to as far as you need to perform the experiment to that accuracy and then send the signal back here, right? So that's the sense in which all ADS vacua are solutions in flat space theory, but not the other way. Okay, you cannot see flat space time from ADS. Because in this sense, we'll say that the string theory on ADS space is very useful because it studies the theory very well using the dual CFT. Okay? But somehow it loses sight of the unity of string theory. That the fact that the different vacua of the theory are actually part of the same theory that we don't see from the perspective of ADS. So here is a lesson for flat space holography. Okay? That recently there have been many attempts to construct holographic dual of quantum gravity in flat space time. Right? So whatever it is supposed to be, it's supposed to be some quantum theory without gravity that captures all the information about the original theory with gravity. Okay. But what we see here is that if type 2 on T6 times R31, which you know is a good quantum theory, quantum theory of gravity, if this has such a holographic dual, then the observables of the dual theory must contain full information on all the theories we mentioned, right? Which means n equal to 4 super Young-Mills, which are dual to type 2 beyond ADS5 times S5, ABGM, right? The 2-0 theory in D equal to 6, which will be dual to type 2 beyond ADS7 times S4, okay? Symmetric product orbifold, and so on. So this basically says that finding holographic dual of string theory in flat space time is likely going to be a challenging but also a rewarding problem. So I think that's
At this point, in some sense, we do know that 11D flat space has this BFSS matrix description.
yes.
So in some sense, what we are saying is that all of these theories are contained in that.
No,
No.
because starting from 11 dimension, it's not clear that we can get here. We have to start from low dimension, right? So the simplest example, right, of this is the matrix string theory, right? Yeah. Matrix string theory is basically a theory for type 2A string theory in 10 dimensions, right? And normally we think of the matrix string theory as some kind of supersymmetric Young-Mills, compactifier and circle, right? And you think of the circle radius as a parameter, right? Or some combination of G Young-Mills and some dimensionless combination of G Young-Mills and circle radius as the parameter of a theory. And that parameter fixes the coupling constant of type 2A string theory, right? What this analysis is saying is that that parameter becomes somehow becomes not a parameter in the n goes to infinity limit. Because in type 2A in 10 dimension, right, we have seen that we can create different regions of coupling constant, right, starting from a given value of the coupling constant, right? So this means that you should be able to do the same thing in the dual theory, right? That starting from a theory compactifier and circle of radius r, we should be able to create regions, or that theory must have information about the S matrix of a theory where the circle radius has changed, right? This I don't think can be seen at finite n, right?
In the same, in a topological way, no? I mean, because just like even in your type 2A, you're fixing some asymptotic.
Yes.
And that is what you can do in the dual matrix theory.
Yes.
You fix that. But then you can possibly imagine a configuration in the infinite n limit where you take some subset of the matrix and there is an effective G string or an effective G string for that, which is capturing the
I agree, but it's not completely clear that that can be done, right? Because this, you have to take the infinite n limit, and this is not a cubed limit, right? This is not a cubed limit, right? So,
in that sense, as they say, you can hide a lot of things in an infinite n matrix.
yeah.
So, yeah. No,
but it will be good to see exactly explicitly how this is happening, right?
Yeah.
The point is you cannot do anything that you like, right? That you can only change the coupling constant, right?
If you have fiction, then you can, I think in the case of matrix string theory and so on, you don't have such a clear dictionary.
Yeah.
I think.
Yeah, I agree. If you have a clear dictionary, then you know that in the bulk what you are doing, right? You are creating a black hole, and near the horizon of the black hole, this is happening, right?
You can kind of reconstruct that.
Exactly.
But I guess unlike ADS safety, the dictionaries here are
less clear. Yeah. See, even in ADS-CFT, okay, let's take n equal to 4 super Young-Mills, right? Somehow in the n goes to infinity limit, right, we should be able to change the coupling constant. Because n goes to infinity limit is flat space time, right? So there, we should be able to create an arbitrary large region where the coupling is different from what it is, right? Now, from the gauge theory perspective, it's not clear how to see this, right? Because you are saying that you can actually change the value of the G Young-Mill at large n limit. You can effectively change the value of G Young-Mills.
not asymptotic value, but perhaps
in arbitrary large region, right?
Because you can again probably nucleate some brains which are
Nucleating brains there create change flux. That you can do, of course, even at finite n, right? Because you can give the expectation value to the Higgs field. But it's not clear that you can actually change the coupling constant, because this is, you cannot even do RG flow, right? Because this is n equal to 4, so beta function is 0. So you cannot even say that you are doing some RG flow to change the coupling constant of the theory.
Yeah, but you're looking at, not there's probably some solution which captures exactly what you are creating.
Yeah.
In the sense that you're wrapping on T3 some grains and then
yeah, see, in the bulk perspective, it's clear what you are doing, right? Because you know that you are creating this region by creating some black hole configuration or some something, right?
to get the corresponding states to that.
Yeah, except that, I mean, again, this is not Hooke limit, it's infinite n. It's not clear how the dictionary works there.
Works in the sense that it probably is.
No, but we have a dictionary, for example, for this 3 graviton amplitude, right?
Yes.
It is some more complicated than ADS-CFT, but there's a particular calculation that we do in the
I agree.
BFSS
Yeah.
to get the 3 graviton
Yeah.
amplitude.
Yeah, that I agree. So that dictionary we have, but to create a black hole, right, with this background, that's a more complicated configuration, right? We know that from the bulk perspective, you can do this, right?
Unlike in ADS-CFT, I think we barely have, in the BFSS description for scattering gravitons.
Yeah, the scattering gravitons,
Yeah, in ADS, we certainly have more handle, right? But even in ADS, I mean, it will be good to see exactly what's happening in gauge theory, right? What is it that's allowing you to change the value of the Young-Mills coupling? Whereas for finite n, we don't expect this to happen. Right? How is large n helping?
So you started with type 2A on R4 times T6.
Yes.
And there we could inside somewhere get 11D flat space.
That's right.
You're saying the opposite, you're not sure whether you can get.
Opposite, I think you cannot, because if the 11D theory is non-compact, if you take a very large internal dimension, from there you can go back. That you can do, right? But if the
it's already infinite.
It's already infinite. It's not compact, right? There it's not clear how to go back.
But could I start with BFSS? Let's say you want to do 11D M theory, but let's say 7 of the circles are compactified. Is there a BFSS matrix model?
Yeah, there is a BFSS matrix model up to dimension non-compact space-time dimension 5. Non-compact space-time dimension 4, something goes wrong.
Okay.
Right, because of the infrared issues. But there are descriptions of BFSS matrix model. Up to.
Couldn't we do that? Like
we could do that. Okay. So the simplest example is the metric string theory, right? Where you have only one compact dimension. There itself, you already see that there is a possibility that you can change the coupling. That's the first place where you have a parameter, you have a modulus.
I don't quite remember the setup there, so maybe I'll ask you later about.
Okay, yeah.
Okay. But if anyone else wants to ask.
The larger limit that you were just talking about is without rescaling the top, the G and
yeah, so you have to keep the G string fixed, right? And in the bulk and take the n goes to infinity limit. That's the limit where you get flat space-time. No, I'm saying that we want to make the asymptotic theory as just type 2B string theory in flat space-time, right? That will require taking n to infinity. Yeah, right. Type 2B theory in flat space-time with fixed G string, right? Because there we know how to change G string, right? There you can construct configurations where the G string will change.
There are no more questions. Let's thank Ashoke. Still definitely not some celestial hologram.
Yeah. Yeah, I don't think celestial hologram is going to be this kind of thing.
I mean, I think the matrix string theory can, but it's probably not useful in that form. I mean, I don't see any in principle objection.
Yeah, I don't think that there's no in principle objection. Yeah, but nevertheless, you don't expect this in normal case, right? Because for fixed n, you don't expect to be able to change the parameters. Somehow, in the larger limit, you are able to do this.
But you you are only focusing there on some sector of the Hilbert space where it perhaps effectively appears as if you have changed the.
No, I'm just saying that
You're not changing the asymptotic.
I'm not saying the asymptotic, but what I'm saying is that any S matrix element that you could measure,
Yeah.
with string coupling different from the asymptotic value.
Yeah, you can measure quite arbitrary accuracy.
Exactly.
But that will be a certain sector of the Hilbert space of the full matrix string theory.
Well, it depends on if you have a finite resources, right? Then you can only explore up to finite sector, and you can do it in this case. Right? So what I'm saying is that
No, I mean, you want to create this bubble inside. So for that, you would have to create a black hole or
Whatever, yeah.
So you focus then on that part of the Hilbert space where you've created that black hole.
yes,
And it's
from a
a-
parent theory, right?
from
But
a
I'm saying that
parent
for the
theory.
daughter theory, right? For the inside of our
Yeah.
right? You have certain S matrix,
Right.
right? And what I'm saying is in the parent theory,
Yeah.
right? Any S matrix that you want to measure in the daughter theory, you can measure it.
I agree. So, but so if we now look at the boundary corresponding statement, there is in the parent matrix string theory or larger in mass theory, there is some subsector which is of that in which if you measure the scattering correlation functions or whatever it is, in that subsector, it is as if
You get a full S matrix
full S matrix
of the theory. So that is not in a subset, right? So you can what you are getting is not necessarily a subset. You are getting the full S matrix of the theory and
of the
of
daughter
the
theory.
daughter.
Yeah, so in some sense, but it's a something. I mean, it's like
It's like
Yeah,
self-
because
it's like-
daughter also contains the parent, right? Because you could start with daughter theory and embed the parent inside the daughter.
You mean in the flat space?
In the flat space. Yeah, not in the end. Right? That's why it's things that are happening in the end goes to infinity.
Yeah, but exactly. So it's a question probably of scaling. Yeah, I agree. It is not the definition of the
Yeah.
but it's like these lattice reductions, lattice theories where in some ways you a higher dimensional lattice theory can still include it by looking at the zero dimensional.
Okay, yeah.
It's really just with matrices. I mean, the matrices, I mean, people do make sense of this reduction, even though it's not like a like reduction. This is by like reductions. So there is possibly, yeah, I mean, the Toff limit is probably a good limit for whatever the string simple, yeah. But there's probably more to it.
So what are you exactly saying about the matrix string theory? So you have some 2D angles for an S1. There's 2D angles and there is N and there's a G angles and there's this radius. N is already taken to infinity. I think so. N is no longer there. There is G angles and there is R.
And some dimension list of
Yes.
of these,
So there is some one dimensionless combination,
which is a string coupling of that.
which is the type 2A on R10, which is GS, and it maps to this one. So now what are you saying?
Yeah, now you are saying that if you start from a given GS,
Yeah.
right? The S matrix of that theory
Hmm.
contains the S matrix of the theory for different Gs,
Yes.
right?
In 10 non-compact dimensions.
10 non-compact.
Yeah.
Which means that this must happen in this 2D angle.
Yes.
That if you take this 3 angles for a given
For
3 angles,
yeah.
it should contain the information about whatever the observables are.
Yeah.
In the theory for defined G.
Yes. Yes.
The same are defined here.
Right. So that you're saying just purely from this side, it's not clear.
It's not, yeah.
How to do.
For finite end, it's certainly not.
Yeah.
Right? And
For finite
some emergent properties are infinity.
What is the precise duality you can? Like
It says GS equals.
No,
But is the duality stated at large?
You know some things about the scattering amplitudes of the string theory.
This is the classical limit of this
No,
duality.
the statement is that everything that you want to calculate in calculus string theory in 10 dimensions can be calculated in terms of 2D angles on this.
But at finite time also, right?
No, I think.
No, infinity.
But what is the finite time theory?
Finite time theory is not.
It's not dual to anything.
No, it's not dual. It's equal to something called discrete axial quantity is part of it.
It has literally no analogy. Like it's not like ADS-TIFR where at large and it's semi-classical or something.
No, because there you have an extra scale.
Extra skill, yeah. So there's an extra parameter to it, extra
No.
variability. So it's literally a large and
Yeah. So, yeah.
But sorry, what would be the configuration here that changes GS? You will create a 10D black.
10D black hole or you can, yeah, you can get 10D black. The same solution that I
But without compactification.
The first solution that I described was not compact.
Was not compact.
Let's
So just take that.
Yeah, let's take that.
the Horowitz form.
Yeah, how is that?
There's D0 plane in R10. D0 plane in R10.
Exactly.
And then that has this flowing electron. And you just scale that up.
Exactly.
And that has some loops. So that's like two states in this theory that have different values of GS.
Exactly.
And somehow here they should also both be there.
Exactly.
But I think I kind of agree with that distribution because what this master body Hamada is doing, right? Like they take some finite and matrix model and they look in some deep infrared of that. Now there are a lot of states, there's a continuum.
Okay.
So, but within that spectrum, they are able to read off, properties of the 11D theory. So practically what can we do here, right? You can set up a lattice gauge theory system for this 2D ambient, right?
Okay.
And study some infrared properties of this. That's the only way practically you will get at it, right? So
yeah,
in the low energy limit, there is definitely information about, I don't know about the flowing one, but the simple thing that is there for the 2 graviton amplitude, one should be able to do.
yeah, I think it will be good to see if one can get the result for different things.
For different GS,
From this.
from this.
But for that, I think you need to create the black hole in this.
Yeah, the black hole in this theory.
Yeah. That, what the dictionary is in the gauge theory, I'm not very sure.
But but this, I think Master he studies the thermodynamics
He
of the
studies
D0 plane.
yeah, he studies
Okay,
the
that's your but not this.